So we're down to the last bit of this. So let's talk about these software-oriented stream ciphers. And so these work with 32 bits or 64 bits at a time, of course, to fit into a 32 or 64-bit processor and be more efficient on a CPU. And so this means block ciphers have padding oracle attacks, which we talked about before. And so stream ciphers became popular to avoid the padding oracles. Although the fact that there's padding is not really a weakness. It's just if you give an unnecessary error message. But anyway, in practice, there were a lot of attacks there, and so people started looking at stream ciphers. So they switched to RC4, and for like the last couple of decades, it's kind of hilarious. People would get hacked with AES CBC, so they'd go to RC4, then they get hacked with RC4, so they go back to a block cipher, then they get hacked with that and go back to a stream cipher. We're sort of like somebody jumping from one leaky boat to another leaky boat and then back to the first boat. That's the way it is. So RC4 was a stream cipher that's very popular, used for a really long time. Now it has finally been pretty much deprecated. Like I said, in the last decade or so, people have found so many problems with RC4, they've pretty much given up, and like Windows won't even let you use it anymore. But for a while, RC4 was the cat's meow. RC4 is pretty amazing stuff. You have an internal state, which is 256 bytes, and you start with just each one of them equal to the number of the bytes, so from 0 to 255, and all you do is you shuffle those bytes like a deck of cards. And so you have a key, and all you do is you take this key and you swap certain bits. So you take your key and somehow you swap a pair and you swap another pair, and which ones you're going to swap is calculated from this with this strange swapping algorithm. And someplace in here goes the key. I think the key is here, N. So you just feed in this key and it determines which cards you're going to swap. And if you think about it, this is essentially the same thing as shuffling a deck of cards. You just mix the cards together, but you're mixing it along to a pattern that is completely controlled by the value of the key. So when someone at the other end mixes with the same key, they will get the same mixed up deck. And now you have a lookup table where every byte can be replaced by a different byte. You have 256 numbers that are random 256. So it will scramble every byte to another byte, and that gives you a key stream. Oh, to generate the key stream. Okay, then you generate another process to generate key streams out of it. But the point is, it's all determined by that key, and you can reproduce it at the other end. And it looks really random, and this turned out to really be fast and really popular, and they used it for all kinds of products for a long time. So used it in WEP, the old 802.11b encryption scheme. Now, the one problem with it is it doesn't have a nonce anywhere in the algorithm. It just has a key. So what they tried to do, this kind of mistake you see a lot, they tried to just call the first 24 bits of a key a nonce. Now this is not the right way to do cryptography. To take a system that doesn't have the feature you need and just take part of some other feature and call it that feature. It's not really the same thing as having a nonce, which we're going to see. This is one of the major, huge flaws of WEP. Another one is the problem with the padding oracle attack I mentioned last time. The padding oracle attack that we do in the project here does not give you the key. It just lets you forge a message which will decrypt to a message of your choice. So you can make a fake encrypted message that will decrypt to one you like. And that would fool a lot of systems because they would take the ability to write a message I can decrypt as proof that you have the key and you're the administrator. And that's not the same thing. Authentication is not the same thing as decryption. So thinking about this more carefully would have saved you. You know, the fact that you create a message I can decrypt does not prove that you were the administrator. That's an authentication job, and there are different techniques for that. And here's the thing. A nonce is not the same thing as a key. And trying to pretend they're the same is not a good idea. So here's one problem. 24-bit nonce is too short. You might think that if you have a 24-bit nonce, you're not going to see a duplicate nonce until 2 to the 24, but because of the birthday paradox, you only have to go to 2 to the 12 packets before you'll see a collision. Because the first one could match the second one, the first one could match the third one, the first one could match the fourth one. So if you have 2 to the 12 random numbers, there are 2 to the 24 pairs of numbers, approximately. So That's 2 to the 12 is only 4,000 packets. And packets are screaming in your wireless network at many packets per second. So in practice, you only have to capture traffic for like 5 or 10 minutes to get a bunch of them that have the same nonce. And remember, the nonce is sent in plain text along with the packet. It has to be. So you can see when they have identical nonces, and then you know you've got multiple packets encrypted with the same key stream, so you've got the same thing as that 2-time pad. You've got two packets encrypted with the same key. And as we've seen, that's pretty easy to fix. So it turns out there's a whole bunch of these. But the other thing about this is, since the nonce is sent in clear text, you know the first 3 bytes of every key. And therefore, you can deduce more bytes of the key. And another thing that makes it even worse, well, you'll see they saw it right away. They saw it within a year or two, actually. So another thing about this is wireless packets are not random at all. In fact, if you turn on Wireshark, you'll see 90% of the traffic is ARP packets, and all the ARP packets are the shortest packets, and 90% of an ARP packet is always the same thing. It's who has 192.168.1.1, tell 192.168.1.100. So most of the bits, you can tell the ARP frames from all the other packets by their size, and most of the bits are known in an ARP packet. So you've got a lot of information. You have the first 24 bits of the key, and you have a whole bunch of things that are pretty much identical being encrypted all the time that you can compare. So it turns out there are a bunch of patterns you can exploit to determine the key, and there's a whole series of attacks. So they made WEP in '99, and by 2001, some of these attacks started happening. And they kept on having more and more efficient, faster and faster attacks. So it's ridiculous. My students used to crack WEP for homework up until around 2011 or 2012, when it pretty much went extinct, when everybody But yeah, they were trying to make something that they could do fast with cheap hardware in the 90s, and they were trying to call it wired equivalent privacy so customers would use wireless networks, because when they first came out with wireless networks in the 90s, customers wouldn't buy them. They said, this doesn't seem secure. My data is just going all over the place. It'd be safer if I had a wire, and that's entirely correct. The customers were correct about that. So they invented this thing saying it was wired equivalent privacy. It's as safe as a wire, and as you can see, that was garbage. It was not as safe as a wire at all. So anyway, RC4 was also used in TLS, and TLS is, of course, the most common, most important encryption routine in the world for all practical purposes. It's the one you use on the internet, which is the vast majority of all the encrypted traffic. So TLS also doesn't have a nonce, but it has a session key. And yep, marketing's a big part of things. See, now you could argue the reason they had to do this marketing with WEP is because the IEEE did not make a standard for encrypted wireless. There was some kind of internal political battle at the IEEE, so they didn't make up their mind about an encryption scheme, so the manufacturers made WEP and WPA. It didn't crypto off. Well, I know. I don't think it went through a proper crypto analysis. I'm not sure about exactly about WEP, but I know that happened with WPA. When WEP was broken, they needed a replacement, and the IEEE did not come up with one for like 10 years. So the industries just made one up. And it didn't really go through, the academics and stuff to test it. So, yeah, I mean, this was not a NIST standard or anything. If it had been, it probably would have been better, because NIST has a proper process. Like DES was not this bad. DES had a flaw, but it didn't have this stupid flaw, So, yeah, it's a good... It would be kind of nice to look at the process of how this happened. Because NIST would never have approved something like WEP. That's my opinion. I don't think NIST ever approved it. Because their process, where you make mathematicians submit it and you publish it all, and all the mathematicians get to attack each other's algorithms, I think it would have caught a lot of these flaws. Anyway, so RC4 has got another serious problem. It turns out that it's not random. The second byte is 0, much more often than it should be. It doesn't really shuffle the cards and makes an equal chance for a card to end up everywhere, which, by the way, I think is also true of shuffling. If you shuffle a deck of 52 cards perfectly, if you shuffle it like 7 times, it gets right back where it started. Something like that. Anyway, so public exploits against RC4 appeared. And supposedly the NSA had figured them out earlier, and they were using them secret. It turns out that all of the first 256 bytes are biased. They're all 0 more often than they should be. So the simplest attack is incredibly simple. If the key stream, all the key stream bytes are more likely to be 0 than any other value. So if you can get the same plain text encrypted millions of times, the most popular value for every individual byte is the plain text byte, XORed with a key stream of 0. So all you have to do is take the most popular value of each byte, and that is the plain text. So that's pretty awesome. And there's a whole series of these things. Many attacks were developed. They kept becoming faster and faster. They had these cute algorithms. Just the same thing happened with WEP, by the way. They had one attack, then they had another attack, then they had another attack that was like a little faster, a little better, a little cooler. It's like glass, once you have a crack, it just shatters more and more. Once there's some kind of flaw that lets some kind of pattern get through, then there's more and more ways to exploit that pattern more and more cleverly. So RC4, everybody's pretty much given up on it. They've said, come on, knock it off. You can't use RC4. Although, most of these attacks do require getting it to encrypt things millions of times. So it's not terrible. It's not as bad as WEP. But it's bad enough that people no longer recommend RC4 for anything. So anyway, here's one that could decrypt an encrypted cookie value in 75 hours if you can make 4,000 requests per second for 75 hours. So, that's not exactly something I could assign for homework. But it's not like it's beyond the reach of anybody. You don't need $1 million or anything. So, all right. So Salsa 20 is another stream cipher. This is approved by a proper European competition to make a secure cipher. And this is the portfolio of the best ones they recommended in 2011. And you see it's got grain here. And it's got Salsa 20. So Salsa takes 512-bit blocks, and it uses a counter. It has a key, a nonce, and a counter. And it runs it through this algorithm, and then it creates a bit stream which will XOR with the plain text. And it turns out that it does it. You have 4 32-bit words, so that's 128 bits, and it mixes them all up like this with left shifts. Just to remind you of that other one we looked at earlier with the weird ANDs and XORs with all these weird numbers. They've chosen to shift it by these, and they've chosen to mix the 4 bits in this way, which turns out to be the effective way. And so this is bitwise. These are bitwise rotations. They're not shifts. Rotating means, if you take this 32-bit word and you shift it 8 bits to rotate it 8 bits to the left, you take the 0, 1 off the end and roll it around to this side. So the 0, 1 goes over here. That's a rotate. Nothing falls off, and you don't need to generate any new bits. You just rotate the bits like they were on a necklace. I think it's nonlinear, but it's a good question. I'm not a good enough mathematician to know. I think that's nonlinear, but I don't really know. But anyway, they use the rotation in this fashion and combine all the 4 bits in this way. So this reminds me a lot of what AES does. Anyway, that's what it does, and it has a 512-bit internal state which mixes all these things together. You have 8 keywords, which are these Ks, and then you have nonce words, which are these news, and counter words, which are here. And these are the constant words, and the T's are the counters. So they've carefully chosen the state to include these 32-bit words, 16 of them to get up to 512 bits. And then you have transformations. This whole thing is very much like AES. So now you have column transformations and row transformations like this that scramble them. Those are called the quarter round functions. And then you do 20 rounds. So it looks a lot like AES in general outline. And so there's a variant that uses only 12 rounds. And if you take it down to 8 rounds, they have found some attacks. So this, you may remember we talked about this a while ago. This is one way to measure the strength of an algorithm. How many rounds can you do that we can still break into? And then how many beyond? So the most we can get in are 8 rounds. So you take it up to 12 or 20, and you have a security, security margin there. So that's the game. That's what it does, and it's recommended. considered a good choice these days. So let's talk about some other things that go wrong. And so, let me try refreshing my screen. It's blurred up on me. And as always, let me know in the chat if you people can't see or hear, but I think it's all right. So, if you reuse the key and the nonce, then of course you got identical key streams, and that's the 2-time pad. That's no good. So you don't want to have that, and that of course has happened. WEP did it by accident, and Microsoft Office did it because they just didn't know any better. In fact, Microsoft did this like 3 or 4 times in different products because Microsoft kept buying companies, and it was not common knowledge in like the 80s and 90s that you needed to have a nonce. So Microsoft would produce a product with no nonce, and then they'd produce another product with no nonce and another product with no nonce because, people, everything goes, it's like tradition. There's a state of the art. Everybody's doing it one way until they all sort of gradually learn they ought to knock it off and do it another way. Like, when I did a lot of Android applications about 8 years ago, everybody was encrypting passwords with secret keys and hiding secret keys on a phone. Like more than half the apps did that. And I don't know if they've learned not to do it, but at some point they will learn not to do it. And it will no longer be the standard. Anyway, here's another RC4 implementation that sometimes sets an internal state byte to 0, so it gradually destroys the state and then stops encrypting. Yeah. And then, of course, there were these insecure export ciphers, which is a huge problem in all encryption. There are therefore products out there using these deliberately insecure ciphers, which can be cracked in fractions of a second, and therefore a lot of products will support those in order to communicate with those stations that are using the export controls. This is why cryptographers are really, really irritated by these export controls. Once you poison the well with weak encryption somewhere, then you create this huge problem that will last for decades, as people are still carrying around these devices that only speak the old weak stuff, and therefore you have to allow some option to turn on that weak encryption, which endangers everybody. It's sort of like the current situation with the virus, right? We're not sending vaccine to Africa and India, so the virus is just spreading, mutating there, making variants that come back and kill us. You can't pretend that the world is not all involved. You can't have some group of people using some old broken encryption, or you now have a system with a big hole in it. So anyway, all right. Let's take a look at the cahoots. 5B. EMV. You mean that's the credit cards, the smart cards? EMV? I hope it has a nonce. Yeah, supply chain's another one, If there's any part of the supply chain that's broken, then you're hosed. That might be enough people. All right, so what system puts a nonce in the key? That was WEP. It's sort of like using a wrench for a hammer. Not a good policy. All right. All right. Which one had a quarter round function? That's also 20. All right. All right, which one uses a session key to protect cookies? That's how TLS works. You make a random 128-bit key, you exchange it with public key cryptography, and then you use a stream cipher to encrypt all the data with that 128-bit key. That's how it works. All right, and which one has 12 or 20 rounds? All right, and that's also 20 also. All right. So we got DSM. I think they might have to tell me who they are, although those might be good initials. And Goodwood Alchemy, I know who that is. And I know who Rohit is. If DSM are initials, my grader will figure it out. If not, you have to tell me who you are if you want your points. All right. Yes, this is a very good question. Why would you use symmetric when you can use asymmetric? I had the same feeling, and the difference is symmetric is faster. That is absolutely the right answer. Symmetric is much faster, like 100 times faster. So you could use asymmetric for everything, but it's just a lot faster and cheaper to use symmetric. That's all. That's exactly right.